Hello, I'm going to present you our paper, Opportunities for Quantum Acceleration of Databases, Optimization of Queries, and Transaction Schedules. First, let me explain our motivation for such a research. We all know the importance of fast data retrieval and storage, and the central role of optimization in database management systems to provide that. In the recent years, theoretical success of quantum computers for optimization problems have been shown, and also the first quantum computers have been invented. Now we have cloud-based quantum computers, but in the following years, we'll also have on-site quantum computers. And all these developments has led us to research the possibility of quantum accelerated database management systems. And we have examined two database problems. The first one is query optimization, which is the problem of selecting the access path and method with the lowest cost. And in this problem, join ordering plays a very important role. So we mainly focused on join ordering. For n tables to join, we have this many possible join orders. So this will be the size of our search space. And a second problem we considered is transaction scheduling, which is the problem of scheduling transactions in queue to maximize throughput, where we have multiple concurrently running cores. So when we're doing that, we have to be careful not to run the conflicting transactions at the same time. We have considered permutation encoding, where each schedule is represented by a permutation of transactions. So for T transactions, we have T factorial schedules, which is the size of our search space again. Both these problems are intractable optimization problems, so there is some room for improvement. So let's see what quantum computing is. It's a computing paradigm using quantum mechanical systems for a speed up, and qubit is the smallest unit of information in quantum computing. And a qubit can be in a superposed state, unlike a classical bit, such as this state here. As you can see, this state of the qubit is a superposition of 0 and 1. And if we measure this qubit, it's going to collapse into either 0 or 1. And the probability of collapsing into 0 and 1 are calculated as the square of the magnitude of their coefficients. If we have two qubit system, then it can be in a superposition of all four combinations, or if we have a three qubit system, then it can be a superposition of all 8 combinations and so on. And if we apply a function to this system of qubits, then we are going to record the output of the function for all of these inputs, which is called quantum parallelism. Multi-qubit systems can also be in an entangled state, which means that the qubits are now correlated. So if we measure this state given here, we are going to get either 0, 0 or 1, 1. So if we only measure the first qubit and get a 0, then we are sure that the second qubit is also collapsed to 0. Quantum parallelism and entanglement are new phenomena that does not exist in classical computing. So they are the reason for quantum superiority. We are now in noisy intermediate scale quantum era, which means that we have limited number of qubits in our quantum computers, and these qubits are susceptible to noise. So we have to limit our computations to a short time. So we have limited circuit depth. Now, cloud-based quantum computing is available, but these quantum computers run on a very low temperatures. But in the recent future, we'll have room temperature quantum computers and also on-site quantum computing with that. So with on-site quantum computing, the latencies will be lower. So now let's look into quantum algorithms. We focused on quantum optimization algorithms. There are exact and heuristic quantum optimization algorithms, and there's a possibility of utilizing these algorithms in the near future. But to do that, we have to be careful about qubit and circuit depth requirements, because we have limited number of them. So we have selected some methods with potential speedups and analyzed their requirements. Let's start with exact quantum algorithms. With these algorithms, the exact optimal solution is found, and they require a function evaluation on a quantum circuit. So this means that we are going to need additional ancillary qubits. An ancillary qubit is a qubit that assumes its initial state at the end of calculation. So it does not keep a final value, but it is only used for keeping intermediate values for function evaluations on a quantum circuit. These algorithms also have high circuit depths, so they are mostly applicable for small problems. So let's see the potential of these algorithms. To enumerate all possibilities on a classical computer, we are going to require order of n functional evaluations, where n is the size of our search space. But with quantum exact optimization, we require only the square of that, square root of that. When we try to solve a mixed integer programming, we mostly use a combination of simplex method and branch and bound method. So in a simplex method, we use classical linear solver, and its complexity is the cube of the number of constraints. But with a quantum linear solver, we can decrease this complexity. Here, this is the number of variables and number of constraints, which are dominating parameters. And as you can see, the order in the manner of these parameters are decreased. In the case that we have a matrix with not very high condition number. When we apply dynamic programming to solve traveling salesman problem, we are going to require order of 2 to the power of number of cities function evaluations. But with quantum dynamic programming, this value is reduced to 1.728 to the power of number of cities. And this method can also be adapted to other optimization problems. Now let's see the qubit requirements for these algorithms. In quantum exact optimization, we search through the whole search space. So we are going to represent the search space, and we are going to need the logarithm of that number of representation qubits. In quantum linear solver, we are going to require logarithm of number of tables plus logarithm of the condition number qubits for join order optimization. And for transaction scheduling, we are going to require logarithm of t squared times c plus logarithm of the condition number qubits. Here, c is the number of cores in our algorithm, in our problem. And for quantum dynamic programming, we are going to search through the subsets of the tables and transactions. So we need to represent the subsets of tables and transactions, and we are going to need then order of n and order of t number of representation qubits. For all these methods, we require ancilla qubits. So the total qubit count is going to be relatively high. Now let's see the circuit depths. In quantum exact optimization, the whole calculation is done on a quantum circuit. So as I said, we require square root of the size of the search space function evaluations. And since both these problems are MP, we can assume that the complexity of one function evaluation is a polynomial of the problem parameter. So this is our total circuit depths, which are quite high. For quantum linear solver, the circuit depth is in the order of, in the fifth order of n for join order optimization, and in the third order of t times 1.5 order of c, which are much lower than quantum exact optimization. So these can be applied for some moderate sized problems. And in quantum dynamic programming, similarly, we require whole calculations, at least the whole search on a quantum circuit, and a search requires the square root of our search space, which is search space, space of the subsets times function evaluations, which is again quite high. Now let's look at heuristic quantum algorithms. With these algorithms, a near optimal solution is found, and mostly objective function is computed classically, so mostly we are not going to require ancilla qubits. These algorithms also have low circuit depths, so they can also be applied for larger scale problems. Now let's see their potential. In nature-inspired heuristics such as genetic algorithm, particle swarm optimization, or Weyl optimization, we start with a randomly selected initial population. But if we apply quantum exact optimization with only a few iterations or only a few function evaluations, then we can narrow down the search space and then select better fitting individual population from this narrowed down space. As we all know, simulated annealing mimics thermal fluctuations of materials, and quantum annealing similarly mimics quantum fluctuations, and it requires a special kind of quantum computer to run, namely quantum annealer. And this method already has promising experimental results. Variational quantum algorithms does not have classical counterpart, but they are hybrid algorithms using variational quantum circuits. A variational quantum circuit is a parametrized circuit which has parametrized gates, and through these methods, we try to find the optimal set of these parameter values. In classical machine learning, we learn the parameters of a model to predict the results of new data points. And in quantum machine learning, similarly, we try to learn the parameters of a variational quantum circuit. And it has already been shown that variational quantum circuits can achieve similar results with classical machine learning using fewer parameters. Now let's see the qubit requirement for these algorithms. For nature-inspired heuristics, again, we use some version of quantum exact optimization. So we have the same number of representation qubits, and also we require ancillary qubits. For quantum annealing and variational algorithms, we use the QUBO formulation of these problems. And in this formulation, joint order optimization requires order of n squared qubits, and transaction scheduling requires order of r times c times t qubits. Here, r is the time span value that is set at the beginning of the algorithm. In quantum machine learning, again, we have to represent the whole search space. So we require the logarithm of the size of the search space qubits. For these three algorithms, we don't need ancillary qubits, so the total qubit count is going to be relatively low. Now let's look at the circuit depths. As I said, in quantum exact optimization for nature-inspired heuristics, we are going to apply only a constant number of function evaluations. So the circuit depth will be constant times the complexity of the one function evaluation. Quantum annealing does not run on a circuit-based quantum computer, so its circuit depth is not applicable. It runs on a quantum annealer, and a quantum annealer takes the computation time as a parameter, and it changes the precision of the calculation. Variation algorithms runs on circuit-based quantum computer, but again, the circuit depth is a parameter, and by changing that, we can change the precision of the result. But for some variational circuits with entanglement layers, the circuit depth would be a polynomial of the number of qubits in the circuit. In quantum machine learning, after training the variational circuit, getting a result takes the logarithm of the in the order of the logarithm of the size of the search space. After this analysis, I would like to present you some open challenges or future research directions in the field. First of all, we can always develop new hybrid quantum algorithms. And for these algorithms, we have to design quantum circuits if they run on a circuit-based quantum computer. But to run them on a computer, we also have to compile these circuits, because each quantum computer has its own set of applicable gates. So we have to represent the gates in our designed quantum circuits as a combination of these applicable gates. We can also develop noise-resilient algorithms to achieve somewhat higher circuit depths. And of course, after designing all these algorithms and circuits, we have to implement them into some database management system and run experiments on them to get results, and so that we can select the best approach for a given problem instance. And ideally, a database management system would select the best approach, quantum or classical, on the run, depending on the given problem instance. And obviously, we can always accelerate other database problems, such as multi-query optimization or index tuning using quantum computing. That's all from me. Thank you for listening.